gonna go live. Okay, in theory, we should be live again. So, hey everyone, welcome to Open Space at a non-standard time again. My guest today is Jason Derleth from NASA's Innovative Advanced Concepts, also known as NIAC. And
Yeah.
I have been wanting to do an interview with the folks at Nayak for a long time. And if you don't know what Nayak is, I promise, I guarantee you're going to want to listen to this conversation. You're going to, suddenly everything will make a ton of sense when you think about the kinds of stories that we talk about here on my channel. So Jason, welcome to my channel. Welcome to Open Space.
Thank you, Fraser. I really appreciate the interview.
So tell everyone who you are and what you do.
So I get the best job at NASA headquarters. I think the engineers out at the centers have more fun than me, but at headquarters there can't be a better job than this. I get to run the agency's most advanced technology development program for mostly space concepts, but also aeronautics as well. And so the NASA Innovative Advanced Concepts (NIAC) is a very small program, a total of about $8.5 million in a good year, and we are sort of, I like to think of us as the venture capitalists of NASA, or the DARPA of NASA, sort of. We look at stuff that's 10 or more years from use, and we give people a small amount of money, $125,000 over 9 months, to do engineering analysis of a new idea to see if it would make sense. And the best ones can come back for a $500,000 grant over 2 years. And now, just this year, we have a phase 3, which is $2 million over 2 years. And so we expect some pretty good hardware to come out of the phase 3, reducing risk for possible future use for some of the most risky concepts. So we look at the high payoff, high risk concepts.
So can you give people a sense of, like, what are some of the things that we're now fairly familiar with, ideas that were originally made their way through the NIAC pipeline? Because
Sure.
there's been so many amazing ideas.
Oh, thanks. I'll do my best. I have memory of most of this program. So NIAC was actually canceled back in 2006. With the last studies wrapping up in 2007, and then we restarted it in 2011. Thank goodness. I think NASA without NIAC is not as exciting. I do believe that. So one of the neat ideas is probably exploring other planetary systems. You've probably talked about Breakthrough Starshot on your show. And Breakthrough Starshot actually originated from, well, Bob Forward had Dr. Forward had a science fiction story about it, and it was proposed to us by Dr. Philip Lubin out of the University of California, Santa Barbara. And he said that if you took a chipsat, something even smaller than a cell phone, and put a 1 meter sort of solar reflector on it, and then shone a whole bunch of lasers on it at really high power, you could go from 0 to almost 0.3 C, so 1/3 the speed of light almost, in about 10 minutes. And the math worked out. I'm not sure that even a chipsat is going to survive that amount of G load, but at that speed, you might be able to get data back from Alpha Centauri in 20 years or so. And you know, as he did his technical study, he slowed it down just a little bit, down to 0.2 C. And he was approached by Yuri Milner during his phase 1 study to help start Breakthrough Starshot. So that was a really good one that went through.
One of the other ones that I can think of is the star shade, the big petal-shaped sunshade that's been proposed for future missions like HABEX, and maybe even to go with the James Webb.
That's right.
There have been there's been balloon concepts for Venus, rover concepts for Venus. There's been an elevator, a space elevator on the moon proposed.
Actually, the first space elevator that was taken seriously came out of the NIAC program. Before the NIAC program came out, the people had sort of laughed at it, but after a feasibility study showed that it might actually work, and there was a place on the Earth where you could do that. You know, NASA's even had centennial challenges to see if climbing rovers could climb up. quite a ways and stuff. So that came out of the first NASA Institute for Advanced Concepts, which started in '97 and went to 2006.
So those are the kinds of ideas. I mean,
Yeah.
if someone ever figures out a warp drive, it's going to come from, probably it's going to come through the NIAC, one of these NIAC
Mm-hmm.
funded projects, you know.
Yeah.
So now, you know, here we are. You said, you know, that I know it had been running. It got shut down in 2007, started again in 2011, and has been running fairly continuously up until
That's right.
now. So what
Yep.
is sort of what is the typical cycle? Like right now where we stand today, how many projects are in various phases of NIAC right now?
So we have, I'm not sure exactly, I think 12 phase ones going. And we have 7 phase twos that are in their first year, 8 that are in their second year, and 2 that are in 2 phase threes. So our normal load is a little higher on the phase ones, maybe 16 phase ones, and around 7 phase twos each year, and then 1 phase three. So that's what we normally get. Um, and we get quite a number of proposals every year, between 200 and 300 for those
Wow.
16ths. Yeah, it's a rough few weeks for us to respond to those effectively and fairly. We try as best as we can to spend time on each and every one to understand what is being proposed and whether or not they can do the work and all of that. And that solicitation has been opening in the early fall up until this year, but I believe next year we have been given the go-ahead to change our schedule and pull it back to the beginning of summer. So I think we'll
Right.
have the solicitation released in June this coming year.
And so what is the process? So you're, I
Mhm.
mean, you have to be an American person or company, and
Actually, you can be a foreign national legally in the United States and working in the United States, so long as your money isn't coming from one of the restricted countries.
okay,
Yeah. So if you're not on the restricted countries list, if you're not receiving money from the
right,
restricted countries list, you could even be a student in a university uh, from
right.
anywhere,
And
and as
so
long as you're legally here.
what are the, like, what is the
Sure.
process? I mean, are you putting out a request for proposals for specific
Yes.
kinds of things? Like you're saying, we want to understand, you know,
Right.
we want some methods of propulsion, we want some new construction methods, we want, or are you just saying, just tell us
Hmm.
your great ideas
Yeah.
and we'll categorize it as we see fit?
Much more the latter than the former. We have a little bit of a stress for the current exploration of the moon listed in our current solicitation, but it's very soft. We ask, you know, right now there is a push to go back to the moon, but we still don't know where innovation comes from. You know, if we knew what innovation was, if anyone knew what innovation was, well, they'd be billionaires and they'd have lots of books sold and everything. I think the fact that there are dozens of books on the shelves about what innovation is, and each one is sort of contradictory, means we don't really know
Yeah.
what innovation is until we see it, and then, oh, that's innovative. So since we don't know, we don't ask for any particular areas like propulsion or anything like that, although we do get quite a few propulsion concepts every year. One of my favorites is a telescope that we got that isn't a space telescope, but it is a space telescope. It's really kind of freaky. The person suggested that we could take a weather balloon and put another small balloon inside of it and illuminize half of that balloon. And in radio frequencies, they go right through the mylar. It's very thin anyway. And so you can fly this weather balloon up to the edge of space and above well more than 99% of the atmosphere, and especially the water lines that tend to block the radio waves. I'm not an astronomer, so I could
Yeah.
get some of the details wrong. But essentially, you're in space with a balloon instead of a giant space telescope. And he actually won a follow-on award from the Science Mission Directorate, not the Space Technology Mission Directorate, but the Science Mission Directorate that flies all of the science missions, to actually fly one of these balloons, a small prototype, but still a fairly large. I think he's going to have a 2-meter mirror up in space, and it's all based on a NIAC. So we do stuff that's a little closer in 10 years or so from original propulsion. So No, we don't have any particular areas. That's the answer to your
Yeah,
question.
yeah. No, it's hard not to totally rabbit hole
Yeah.
on these different ideas, and I will
Yeah.
I guarantee I'm going to do the same thing. I'm sure I will talk about stingray shaped airships that could be flying around on Venus.
Dr.
Don't worry,
Bayandor, yes.
I just did a video about it. It's going to be coming out in a day, so you don't have to
Oh,
worry,
cool.
everyone. Yeah, um,
That's a fun one.
yeah, super cool. Then and so people have an idea. You have this period where there's a request for proposals, and then people will submit. And so how many proposals will you receive?
So we actually are very aware that it takes a lot of work to propose to the government for a grant. And so we try and lighten the load as much as possible. We ask for a 3-page white paper. Now, that 3-page white paper has to be in the correct format and it has to go into the government systems. So you have to be registered with the government systems and all of that. But once you've got that down, 3 pages isn't too hard to write about something that's really fun and interesting, we hope. And what we do with those 3 pages is in the program office, we look at each one and decide whether or not it's in scope for the program, because we're not allowed to do piece parts or widgets. Or a good example would be there are a lot of really interesting and really good new metamaterials that are being built. And people will propose to us and say, we will go into the laboratory and we will build a metamaterial with a following lithography process. And then we will come and we will test it until it fails a crush test and or whatever sort of destructive test they propose. And then there will be this new material that people can use. We take the C in NIAC pretty seriously. So we ask people to take their widgets and show NASA, show everyone in the aerospace community why you would want to do this thing. And so don't tell us about your material so
Right.
much, but tell us how that material would make a mission better. And so pick a mission, whether that's entry, descent, and landing at Mars for a robotic lander, or if it's cleaning the air for humans in a human cabin while the cabin is going to Mars, or if it's spelunking into Jupiter's atmosphere, or exploring one of the icy moons. Whatever the mission is, you can make that up. As long as it's in the realm of possibility for NASA to look at in the future. And then show us how your new material or your new widget or your new actuator, whatever it is going to either make that new mission possible or greatly improve an existing mission by an order of magnitude or more, or make a current planned mission or a possible future mission less expensive. That's one that I like to see as well. So if you're, an order of magnitude less expensive, well, eventually maybe that Dysonian sphere will be possible, or whatever it is that you're proposing, right?
Yeah. So then, okay, so then you get several hundred proposals.
Yeah, 200 to 300 proposals.
300 proposals, and
we
then
turn those around in 4 weeks to 6 weeks.
Okay.
And invite a full proposal from about 75 to 110. It depends on the year, however many good ideas we have. And the full proposal is you add on another 5 pages. You keep the first 3,
right,
and the 5 pages are more of a work plan. And who are your people going to be? How are you going to complete the work? How much money is each step going to cost? Are you going to is the amount of work that you're proposing commensurate or appropriate for the amount of money that you'll be getting? That sort of thing. We've had people propose, oh yeah, and we'll bring you a prototype of the human-sized rover at the end of 9 months with 125,000. No, you won't. No, I'm sorry, you're not going to be able to do that. It'd be great if you could, but no, you can't do that. And what we're looking for in the end is really a piece of research that can be put up on the shelf, and we put them up on the shelf.
Yeah.
Unlike other programs, we actually take a final report that is more than a couple of pages long. We actually ask for sort of a full technical debrief of what you did. And then we take that and put it online.
Yeah, and can confirm. Again, many of the videos that I've done here on my channel use one of those reports as the anchor or feed into that, and the reports are very readable, very accessible to me
them.
Most of them, are very accessible. They're often very lengthy. They have great pictures. They go into a lot of detail. So just to sort of follow the story again, so you've got the 75 to 100 people that you have requested a more in-depth paper.
Sure.
They add another 5 pages to the original proposal, essentially fleshing it out in ways that are interesting to NIAC.
Right.
You get those papers, and then you make a decision on who.
Well, we actually bring in technical panel reviewers at that point. So each of the full proposals is reviewed by at least 3 different technical reviewers that are experts in that field. And we've had people that have been center directors in those panels and things like that. It's just an unbelievable resource of folks who are interested in NIAC. It's fun to review these things, so we can get really good people to come in. At that point, after we've winnowed down to say 30 or 40, then we take that to the source selection official. After we check with the rest of NASA quickly, we have points of contact at the Science Mission Directorate, at the Human Exploration and Operations Mission Directorate, and at the Aeronautics Mission Directorate. We check with them to make sure that this research is not necessarily interesting to them, but doesn't overlap with something that's already been studied. And we've had people come to it. We've gone to people at that point. Yeah, I funded something like that back in 1987, and there's a video of it online. Here you go. And oh well, I guess we can't select that one then because it's already been done. But other than that, if they're interested in it, that's great. If they're really uninterested in it, that might be great too. It depends on what the subject is.
Yeah.
I can think of one particular one, which is human torpor, which is, we've always heard stories about cryosleep. We're going to cryosleep ourselves to the next star or whatever. Nobody had ever studied it on an engineering scale. What would a spacecraft look like? Would it actually be lighter? Would it be more efficient? Or would all of the cryosleep stuff take up so much space and be so intensive that it would actually be less efficient? And trying to remember, SpaceWorks Engineering, I think, is the name of the company.
Yeah. I
And
did a video on that.
Yeah, it's a really neat one. I can tell you that there were folks in the office, the health and I'm trying to remember the name. I'm sorry, I can't remember it right now. But the basically the astronaut doctors.
Yes.
Were not very pleased with this one. They didn't think it was necessary. They didn't think it would be useful, and they didn't think astronauts would agree to having a peg tube in their stomach or anything like that. And they might very well be right about all of that. But it's interesting to have something like that up on the shelf so that we have a reference for the rest of time to see what that would look like.
So you've got your 7,500 people who have come back. You then offer them to compete for that stage 1. Is that when you launch the stage 1 is based on that more in-depth report?
That's correct. So let me go over from the beginning again because I keep getting sidetracked. So we get 200 to 300 proposals depending on the year. We winnow at the program office. We winnow those down to 75 to 110, somewhere around there. Then we have expert panel reviews on the 8-page proposal. We invite those 75 to 110 to give us 8-page proposals. We review those with expert technical panels. We check for duplication on any that have not been eliminated by the technical panels. And we go to the source selection official who chooses the final 16 out of the top contenders. And then we offer those folks the grant, which is $125,000 over 9 months, sort of a quick turn of the analysis crank to see if their idea is actually feasible.
And so what are you looking for them to deliver in that 9 months and 125? And I mean, just to sort of compare, like that is the amount of money that you would spend for a researcher or two to spend full time doing the math, thinking about a problem, and actually writing up a report. So, I mean, anyone who is out looking for fundraising, that's a reasonable amount of money to be able to take your idea to the next level. So what are you looking for them to report for you? What do you want them to bring back?
So essentially what we want is, here's this neat idea that I had. and it's going to work or it's not going to work, and here's why, and then here's the documented technical procedure that I went through to get to that answer.
Right.
And I can think of a couple that have been failures, quote unquote failures, right? Because frankly, in an early stage technology development program like this one, finding things that don't work is appropriate, right?
Yes.
And we've only spent $125,000. Let's not go down that rabbit hole for the rest of time and spend billions to make a spacecraft. Let's put this on the shelf and let people look at the research and try and do better next time. But that's basically it. We're looking for a report. I think of this as on the level of a master's degree at a technical university, anywhere between 50 and 150 pages, describing the idea, telling us whether or not it might work, and then why and how they got to that answer.
Right. And again, when you look at any one of these reports, you're seeing, like, I can think of examples as well. Like, say, people always want to know if there's some way to make an artificial magnetosphere around a spaceship to protect astronauts from cosmic radiation. And so someone is doing the math. They're figuring out what kind of magnetic field would be required, how much energy that's going to require, what the various Gauss levels you're going to get at different sizes, what could be the potential side effects, comparing that to existing materials and coming with an overall analysis of what it might take and what are some configurations of putting out the coils that will do the trick. And so, that is all encapsulated into the final report that's delivered to NIAC. And as you said, you take those things, you put them up on the shelf. So we've got you to phase one. Right. What happens now to go on to phase two? Do you open it back up again, or are you actually just following up with the people who delivered phase ones to go on to phase two?
So we open it up again, but only to people who have successfully completed a phase one final report. So once you've completed that, then you can propose. Now, what we do is we allow people to propose multiple times. So if they don't succeed one year, they can learn from the comments from the technical panel reviews, improve their proposals, and then try and propose again. There's one gentleman, I should say also that we're open to anyone in the United States legally. You don't actually have to be in the aerospace field. We had one guy, Anthony Longman. He's an architect. He's not an aerospace type person. He doesn't have an engineering degree. He's an architect. And he said, there's this guy back in the 60s, Buckminster Fuller. He created this thing called tensegrity, and nobody knows really how to use tensegrity. And so you find all this art made out of tensegrity, and that's it. That's about it. But I think you should make spacecraft out of it. And the reason why is you can make the structure as much as 93% less massive with the same amount of strength. And that's a big deal. And he proposed, and he failed, and he proposed again, and he failed. And by the way, he called me and talked to me after each time, and I tried to coach him in between. Yep. Legal for me to talk to people. As long as there's no open competition, send me an email. I'm happy to talk to people and help you understand the program and how to propose to it and all of that. Anyway, on the third try, he won an award for a tensegrity habitat that might, and this is a big might, be 2/3 the volume of the entire International Space Station at first launch.
Right.
It's really an incredible thing. And what's been amazing to me is watching him, because he took 3 tries to propose to phase 2 before he won a phase 2, and he's wrapping up the phase 2 now. So we'll have a new report from him up online fairly soon, although he's a co-I on the second one, and not the PI, not the fellow, the NIAC fellow. Dr. Robert Skelton is the NIAC fellow.
So do you have a set number of phase 2s that you're looking to fill, like a set budget, or is it kind of just whatever you folks think is appropriate, to whatever's ready?
We try to choose stuff that is really exciting as well as almost ready. And for the phase 2s, there's still a lot of risk left in these things. And what we do is we try and time all 3 phases of the program to have selection on the same day, so that if we have a particularly strong group of phase 2s, we can choose 1 extra phase 2 and 2 fewer phase 1s, or maybe an extra phase 3 and and fewer phase 2s and phase 1s. Or if it's a great initial crop, we might choose 20 phase 1s. It's a really interesting little thing, and it's up to the source selection official, who is one step above me at headquarters. So
Right. And then the new addition that you've added in the last couple of years is this idea of the phase 3. So what distinguishes the phase 3 from the phase 2 projects?
So the phase 2 is kind of a unicorn. It's hard to explain. I like to start out talking about phase 3s by saying phase 3 doesn't really exist. The goal is to create so much interest in phase 1 and phase 2 that, in fact, you don't need a phase 3. Someone like the balloon reflector can pick up and run with your phase 2 at the end of the phase 2, or maybe even at the end of the phase 1 if it's just really that exciting. A phase 3 is for something really difficult that is obviously good to do. And we have two right now. One is Dr. Joel Sercel. He's talking about mining asteroids. And he has set up a sort of a preliminary small spacecraft that's CubeSat sized that would be able to launch its own synthetic asteroid and then go catch it and mine it and then use the water that it gets to thrust around, to sort of a full proof of concept.
Yep.
But something like that still, even though it's CubeSat size, is not cheap. And there's too much risk for the science mission directorate or for the human mission directorate or even the space technology mission directorate to go forward with such a, maybe it's a $10 million mission, maybe it's a $6 million mission. And so we're sort of trying to bridge the gap with this phase 3. The idea is he can get enough done in the phase 3, reducing the risk that someone will come along and say, hey, you've gotten most of the way to that phase, that prototype mission. Why don't we throw in $4 million and we're going to try and do that mission. Right. It's really exciting. And he actually partnered with another company, Momentous Space, and they threw in $1 million of their own money, paying their own workers. So it's an in-kind contribution. But so that it's already $3 million of nominally a $6 million mission. If everything went well, they're going to be half done, and they're going to eliminate a whole bunch of risk before they're done with their 2 years. Our second one is a little bit closer in a way than asteroid mining. Red Whitaker, Dr. Whitaker up at
he's at Cornell.
No, Pittsburgh. What? Why am I having Carnegie Mellon?
Carnegie Mellon. That's right. Yeah, he's part of the robotics. He's the one who worked on the on one of the DARPA self-driving vehicles. Yeah.
Yep, he's the one that won the DARPA challenge. Yeah. He also was the one, as a fresh out from college. He went to the Department of Energy after 3 Mile Island and said that he could map 3 Mile Island's radiation levels really a lot cheaper than Westinghouse Corporation could. And he actually won that bid, and he did more than just map it. He did a really great job. And that, I mean, when you start your career off with something like that, you're bound to do even more. And he has. His current push, he's the founder of one of the companies, Astrobotic, that won a CLPS Award, Commercial Lunar Payload Services. So the idea is that NASA can put out a bid to these 8 or so different companies that have promised that they will be able to land things on the moon, and then they will compete. Those 8 companies will compete for each one of these things and say, well, we can do it, and they're guaranteed a certain amount of money over the period of the CLPS award. Astrobotic won an award for phase 1 back in 2011, actually, for pits and caves exploration. Yeah. So the idea was we would create a rover that would go down into these pits and caves, which are very important targets, not just for science, because you can see the strata as you go down through these pits and caves. So you can really gain a whole lot of information about geology of the body that you're on. But it's also interesting for humans too, because we've talked for a long time about how you might be able to use a pit or a cave or something that had a skylight in it for a human habitat.
Yeah.
And so he won a phase 1 and a phase 2, and he proposed to the phase 3 when it opened, and he won, but not for exactly the same thing. He's doing a step in between spelunking into a cave. He's going to land a rover on Eclipse platform. And this, by the way, is a Carnegie Mellon Award, not an Astrobotic award. But land a rover near a crater, drive over to the crater, and autonomously circumnavigate this crater and build a full three-dimensional model of the crater while circumnavigating the crater, all within the 2-week daylight period.
Right.
Because we know that rovers don't generally survive, even landers often don't survive the 2-week lunar night. So all done autonomously, and really an interesting mission with essentially a cube rover. I mean, I don't want to quite call it that. I think it's a 15-kilogram rover. Yeah. Very small, about the size of maybe a 6U CubeSat, something like that. And he won because he's partnered with Astrobotic, and they will actually propose the mission back to the CLIPS program. And so they will say, we can actually do this thing. And I'm hoping that NIAC can be the first program in NASA to land a rover on the moon since the push to go back to the moon. So that would be really exciting.
So, I mean, and this sort of now, this conversation kind of leads into sort of the next path that I want to go into. And, my experience, my observation from NIAC from afar is there are a lot of really great ideas that get proposed, very exciting, the kinds of things that really capture the imagination of the public. I mean, the whole purpose of having public relations with NASA is to show, I hope, to show the taxpayers, to show people what that money that they're giving goes into in the kinds of programs. And the kinds of NIAC ideas are absolutely some of the most exciting ideas that are out there. But at the same time, it feels like it's a much more difficult journey for those to go from a really amazing concept to something that's actually incorporated into existing mission hardware. We've talked about a couple of projects which have come a long way, but still. So do you find that the idea gets, some pieces of the idea get absorbed into some existing mission that's already in the works, or does it, or will it actually sort of cause the germination of a new mission that maybe nobody had ever thought of because they had never thought that it was possible or reasonably inexpensive to do?
So I think the answer is yes.
Yeah. Which one is it trending towards? Which one is
which one is more frequent? That's a good question. I don't know. The example that I can think of immediately about the second, where you sort of work into something that's existing, is the Spheres project that was run out of MIT. Given enough time, I will eventually remember the person's name. The basic idea was that there would be these autonomous little robots that used cold gas thrusters to float around inside of the space station and do stuff, and interact with the astronauts. They remind me a little bit of the back in Star Wars, the New Hope, right? Episode 4, when Luke Skywalker has a sort of lightsaber practice inside the Millennium Falcon. This little sphere bot, right, is one running around and shooting lasers at him, and he's blocking them with his lightsaber. They're about that size. They're about that shape. They're pretty neat. Dr. David Miller of MIT was the PI on this. And that actually ended up being based on a little bit of NIAC work that he did originally back in 1997, and then it eventually flew on the space station. It was modified and changed, and it was only the germ of the NIAC idea that ended up flying. And then more stuff was proposed. He proposed one on magnetic coupling and things like that. But then we have the example, like I mentioned already, of the inflatable balloon reflector, which is 100% whole cloth NIAC, flying in its final configuration in 2021. It'll fly as the NIAC mission. And I can think of a few others that it's going to be an amalgam if they ever fly. But you mentioned the Venus rover. There's the Clockwork Venus rover that we've studied out of JPL, where it's essentially a giant wind-up clock, right? And the wind winds it up, keeps winding it up, and it's all mechanical. The mechanical rover can go for a very long time, maybe even years in the Venusian environment, which is very punishing. So if that ends up flying, though, my guess is it's going to have a cool electronics box. Normally we have warm electronics boxes, but this is Venus, right?
Yeah.
So it's going to have some electronics, is my guess. It's going to have a camera, probably a real camera and not just a mechanical camera, but maybe. But it's going to need a way of communicating back to the Earth. And that's almost certainly going to have to be electronic eventually, although there are some ideas for communicating with mechanical means. But my guess is that if that flies, it's going to capture the imaginations of the Venus community, and they're going to say, hey, really, we could rove around on the surface of Venus for weeks before the vehicle dies. This is worth looking at, because right now the longest probe that we've had survive at the surface was, I think, 36 hours.
Yeah,
No,
yeah, one of the Venera landers. Yeah, and they all
might have been 136 hours.
And the joke that I always make is like half the transmissions we got back is just robotic screaming, right? So
yeah, exactly. So that'll probably end up, if it captures the imaginations of the people that are big in the Venus crowd, they're going to incorporate that into what they're already planning.
Yeah,
to make what they're already planning better. And I can imagine other missions like the Titan submarine. Again, it's pretty complicated to send a submarine to Titan. It might happen, and if it does, that would be really, really cool. Yeah, methane ocean, right?
Yeah,
it would really awesome. And it can do more science. But what might end up happening instead is maybe a boat.
Yeah,
I don't know. A boat would work for 90% of the science. And
I saw a sailboat idea, which I liked. So, I know that NASA and other space agencies, they have this. There's always this balance, right, between going with tried and true technologies, chemical rockets, existing RCS thrusters, even certain kinds of toilets that are used in the International Space Station. Like there are known ways to do this. And a lot of times I think about technologies like ion engines, and it took a real leap of, even though that technology had been developed and it was tested in the lab and it was really shown that ion engines worked like a charm, it required a very innovative spacecraft. It was the Deep Space One spacecraft that, with a whole bunch of different test suites on board, that somebody was finally, okay, we'll put an ion engine to see if this works. And now the ion engine, every spacecraft is being considered to put an ion engine, because why not, right? All the Starlinks have ion engines. Like, they make a ton of sense. If you want to move in space, you add an ion engine. So on the one hand, you've got all these innovative ideas that sit on the shelf because mission planners are too nervous to add this kind of technical risk to their missions. But then on the other hand, you've got things like the James Webb Space Telescope and the Space Launch System, which are years late, billions of dollars over budget. And one of the main reasons of that is because there was a tremendous amount of technical risk that was knowingly introduced into the project, that they knew that creating a gigantic fold-out sun shield, a rocket at the scale of the Space Launch System, that was technical risk. And what do you know? Big surprise, technical risk introduces higher budgets, longer time frames. And so it's kind of like it feels to me, watching this whole thing unfold, I always see two conversations happen again and again, which is, why doesn't NASA take any risks? And NASA takes too many risks. Right?
Yep, you're right.
So what is the solution to that? How do you take more and less risks? Whatever it is, take the right amount of risks.
Well, and technology development is a real risk, right? Because it's people. I did a report for quite a while back in 2005 for research and technology portfolio planning within the agency, and in that report we looked at how the incentives are completely different. But what's really interesting to me is that the technologists speak a different language than the mission planners, okay, and the project managers. The technologists will come in and I can get 4 times the performance, and I can do this and that and the other. And the mission manager or the project manager says, whoa, whoa, whoa. How much does it weigh? How big is it? Is it going to fit in my box? How much power does it use, and how much data does it produce? That's all I care about. Because go talk to the scientists. As if they want something, they'll tell me. And there are ways of getting these people to sit down across a table and getting them to talk the same language that are very effective. I think there's some folks around the agency that have been doing it for dozens of years very successfully. I think of JPL's Steve Pruscia primarily for that. He's integrated new technologies faster than anyone else that I've seen. But surprisingly, the Naval Research Laboratory is also very good at it. They fly new technologies on every bird. But before we go on, I do have to say, when I worked at JPL back in 2003, I was working on MSL, and we were tracking 33 new technologies going on to MSL. And on the one hand, yes, we're afraid to take new risks. On the other hand, we take new risks all the time. And yeah, they can get the system to be sort of wrapped around the axle. And I'm not sure how to do that better other than to fail fast and fail forward, right? You do it when your team is small. One of the challenges that, I've never been a part of James Webb, so everything that I say here, take it with the grain of salt that it deserves. But one of the challenges is that they were designing new technologies as part of the Phase A mission. So Phase A is when you do the mission definition. Phase B is when you're sort of getting ready to build. C is build. D is assemble and fly. Phase E is operations. NASA Systems Engineering Handbook 101. Yeah, it's all downloadable online. But the way that the mission was designed is that they were going to have a lot of different technologies being developed while they were doing the design. And every time that the technology doesn't come through, then you have to redesign slightly. You have a large design team during Phase B, and they were still having problems with the technologies, and they would have to stretch it. And then Phase C comes and they go to build, and you've probably heard that when they went to extend their sunshade, it got a tear in it and everything. Well, now you've got the entire team, and you have to stop assembly and test while the entire team is working to fix everything. And it's all interrelated. I once had a chance to ask Pete Teisinger. He was the project manager for the MER rovers while I was working on the MSL rovers. Why don't we just fly more MER rovers and put different instruments on them? And he said, well, first of all, we're not a spacecraft factory, okay? We make one-of-a-kind, amazing pieces of technological art and send them to other planets. That's what we do at JPL. Okay, understood. But second of all, they're so finely optimized that if you change anything about those instruments, we essentially have to do a full redesign of the system anyway, because it's going to rattle through the system and everything depends on everything. And so, you talk to a loads person and you say, well, if I made this change here, what would happen? And the loads person will say, almost every time, well, some of the loads are going to go up and some of the loads are going to go down. I've got to go run my finite element model to tell you what the answer is. So, and with everything depending on everything else, James Webb especially had a real challenge to get everything to come together and bolt together and have all the bolt holes in the right place, because the technology development was so deeply embedded within the mission development timeline. Now, lesson learned, try and have your technologies to TRL 6 before you enter Phase B of your mission design, if you can, and that helps a lot, right? But I remember I got the chance to work on the Exploration Systems Architecture study in 2005 under Mike Griffin. Dr. Griffin was the administrator. And he flat out said, look, we've been to the moon. We don't need any new technologies to go back to the moon. Don't do any of them unless you see real reason to do it. And, it's funny. Computers have changed a little bit in the last 50 years. And everything else has too, including, well, everything. You can't use the same reentry material because it's bad for the environment. So bringing the capsules back in and having that plasma ball around as the astronauts are reentering Earth's atmosphere, well, that plasma ball is carrying away a lot of the material from the heat shield. And so if it's bad for the environment, it's getting up into the upper atmosphere and going all over the world. Can't use it anymore. Have to redevelop a new one. Guess what? Technology development. And I mean, it goes on and on and on for Apollo. And we ended up reducing the budget some under Griffin, but not a lot.
So, I mean, at the same time that, say, NASA is doing its developments, there is this real revolution in rocketry that's going on around the world. A lot of these concepts of reusable rockets. I mean, the Falcon 9, how it's able to reuse boosters. Obviously, the Falcon Heavy, which uses, I think, reuses 80% plus of the entire rocket with the 3 boosters. Just the upper stage is being disposed, and then who knows what? I mean, I guess maybe you know what's going on with New Glenn, and that's just the tip of the iceberg. There are a bunch of other reusable rocket companies working on stuff, as well as what's going on in Europe and going on in China. Like, this is, if you don't make a reusable rocket in 20 years from now, it's going to be kind of too late. Or sooner. And then you're looking at the possibility of a thing like Starship, where, this thing is going to launch, one Starship in theory is going to be able to launch more than the sum capability of all rockets ever launched ever in the history of humanity. And this is just going to be one, and they're going to build 100, whatever, right? So when, and you must just drool, you must just salivate over the potential, because a lot of the times it's that launch cost that just defines whether or not you can take these kinds of risks. What does dramatically dropping launch costs do to the kinds of projects that you're thinking about?
Well, I've often pontificated on this subject, so you'll have to forgive me if I go on.
Well, we've got like 13 minutes at the most, but try not to use it all, because I'd like to get some other questions in edgewise. But yeah, absolutely. How does it? Because I mean, I think people always. Sorry, I was going to say one last thing before I let you turn you loose. Is that people always complain to me? They're like, "Oh, SpaceX is going to eat NASA's lunch," right? No, NASA is SpaceX's biggest customer. And the more low-cost providers that more low-cost rockets that SpaceX can bring to NASA will buy them and then fly more missions, because they'll be able to fly twice as many missions or 3 times as many missions. So don't worry about anybody eating anybody's lunch. Like, this is a bargain basement sale price that NASA will absolutely take advantage of. But so how does that change some of your thinking?
So I used to say a lot of the times that we keep solving the wrong problem really, really well. I mean, astronauts need radiation protection, and so we bring all this plastic up to try and put it in between the astronauts, and we make things heavier and all of that. Well, gosh, if you could just make a habitat that looks kind of like a Stanford torus, okay? If you could bring up enough mass to make a Stanford torus and rotate it for gravity, right? It's relatively stable because it's a torus in the rotation. You bring dirt or chew up some asteroids if you can, right? And put that dirt on the inside. Well, now you're blocking quite a lot of the radiation right there. If you can line the hull with water, you're doing it on all sides at that point, right? And if it's a large enough habitat, you can grow your own food. And so you're closing the life support loop, where we keep looking at how to close the life support loop with chemicals or with better machineries. And well, gosh, the Earth has a closed life support loop, we hope. And so if you could lift enough mass with a new paradigm of a spacecraft, you could solve most of the problems that NASA has been worried about for 50 years.
Yeah.
One fell swoop. But getting people to think that way is an entirely different challenge. And that's what Anthony Longman's habitat has turned into, is sort of a, let's solve all of those problems. And I hope that he gets a chance to find out more about the New Glenn, because I don't know much about it at all. But he knows people who know people who probably know something. And one launch from that might be sufficient, or a Starship launch might be sufficient to create a whole habitat. And if Joel Sercel is off mining asteroids for water, he's going to have a whole bunch of regolith ready to line these spacecraft. And we are 2 paradigm shifts away, or 3 if you count the launch cost that you're talking about as the first one, from large colonies in space forevermore. I mean, right. We're really that close. And it might be 50 years, it might be 100 years, or it might be 10. I can't tell anymore. Right. I thought that it was going to be 50 to 100 years before Anthony Longman got any traction whatsoever. And he said, oh, yeah, we're talking to billionaires about buying flats. You know, I mean, they don't mind spending $10 million for a flat in space as long as they can get to and from it really easily. Oh, well, gee, I had never thought of that. That's really brilliant. Very cool. You got a flat there for me? No, yeah. Probably not. But
spare bedroom.
Yeah, exactly. I'll sleep on the bunk bed. That's fine.
Yeah.
The challenge though is getting those people, is getting all people to reframe their thinking. Those paradigm shifts are pretty wild shifts, but it all starts with being able to lift all of that mass inexpensively. I have a friend, he's in the chief budget office, code B is what they used to call it. And he had a graph that he could, in 3 minutes, explain why launch prices were staying as high as they were in the 2000s. And what would happen as soon as somebody provided one low-cost vehicle. And suddenly there's a real push to get everybody lower cost. And it had to do with the Department of Defense needing the high reliability that they need for the MILSTARs as well as everything else, right? And human launches from NASA having to be very high reliability. Well, once you can start building stuff that you don't care if it blows up and you make it cheap, you get better at it, you don't blow it up anymore, and you gain the reliability through both repetition and reuse, right? Which is what's happening as we see.
So you mentioned a couple of paradigms. So I've been sort of going on about a bunch of paradigms on this channel, and I wonder if we were thinking about the same paradigm. So the first one is that idea of reduced cost of launch. The second one is the idea of resource acquisition from space, ISRU, in situ resource utilization, pulling, as you say, water from space, regolith, water, heavy metals, all kinds of things. And then the third one is space-based manufacturing, actually constructing and building things, assembling, constructing things in space. You know, things like what Made in Space is doing with their work with the Archinaut. You know, this idea that you could, as you say, take you could take water and carbon dioxide, turn it into methane, turn it into plastic, turn that into, you know, from carbon and water, you can make plastic. And then you can be turning that into struts for a space telescope of any size. And at no point did any of this stuff come anywhere from planet Earth. And you're just building this stuff up in space. And I feel like we're going to be entering an age where rockets are no longer necessary, because all you need to do is, like, the people will want to fly to space, but everything else will come from space. Nothing else holds a candle to the cost.
Well, and what's really funny, we had one gentleman, Mark Cohen, did a study for robotic asteroid prospecting. And he did a full economic analysis at the time of what would make a profit in space if you were able to move things around. The answer was water. Water is important enough that you can actually make a profit by mining water and bringing it with you. Well, by golly, it's pretty cheap to pull some of that carbon along with you, or just plain old regolith. You don't have to do any processing at all. Just bring the broken regolith with you. It's free. Because you're bringing all of that water, which is what you're selling. And now you've got this other resource that's free that you can, they're not going to give it away, but pennies on the dollar, so to speak, right? I mean, it's not the same thing as the water. So you might actually be able to create that in-space manufacturing platform pretty easily once maybe Joel Sercel or someone else manages to start pulling water out of asteroids. So.
Yeah, and I've heard I mean, some of the new discoveries with OSIRIS-REx, when OSIRIS-REx was coming to Bennu, it was getting sort of smacked in the face by debris that was coming off because water vapor was sublimating out into space from it. So turns out there's a lot of water in these things. You just have to grind them up and get at it. So the inner solar system is actually a lot wetter than anyone ever anticipated. So it's good news for all of that. So have there been ideas that you wish somebody would propose? Are there themes that you're excited about that you just haven't seen enough thought put to them yet? Or
it's interesting. No, not really. After seeing all of the different areas of technology development, basically NASA divides it up into 15 different technology areas. We get stuff proposed from almost every single one every year. People are really creative, and they're ahead of me. Usually I'm lagging one year. So we get the new proposals in, and hey, I'm seeing a lot of 3D printing. This is 2012 or 2013. 3D printing in space. Who's this Made in Space company? They put in a couple, and they won an award for a really neat idea of possibly creating little cities in space. Interesting side note. You talk about rabbit holes. There's a Disney show called Miles from Tomorrowland. And one of the bad guys lives on an asteroid that the authors modeled after the Made in Space asteroid. Not, it's just directly inspired by that particular concept. Our program manager met some of the writers for that show at a conference and got into talking to them, and they did a little idea exchange, and they borrowed that idea and put it up. It's pretty neat.
That's awesome.
Yeah, it's really cool. It's a good show if you have kids. But I mean, I would say something like von Neumann machines or whatever the correct term is, but we get proposals on that. Just haven't really seen them good enough to be proposed.
Self-replicating. You want to see some self-replicating robots? It's funny.
I'd love to see that.
I worked for the X Prize for a couple of years. We were doing a sort of an online platform where anybody could essentially propose their own. It's Hero X. They still do a lot of work with NASA, and I was the product manager for the software platform, and so as a test, I put together the self-replicating robot challenge, which was that I wanted people to, whoever could make the robot make the most of itself the next year. Each time we would run a challenge and have robots try to build themselves, then whoever could get the farthest along would win the prize. So now that I know that's in your thinking, I'll see what I can do to get that cranking again, because it would be, that's the key, right? If you can get robots building robots out in space, out of parts from space, then it just all takes off. Jason, this has been absolutely fascinating, and I hope this gives people a chance who are listening, and as you said, they're in the aerospace community, or maybe they're not, but they want to be able to propose great ideas to NASA and to the NIAC program and sort of help that technology find its way. This is the on-ramp. So for people who are trying to think about calendars, what is the next big date that they should be keeping an eye out for?
So June, probably the second week of June is when we will release our solicitation. The other thing is in September, which has already passed, but obviously next year, we have what we call the NIAC Symposium. And what that is we have all of the fellows come together at a big meeting that we open to the public. And we have them present their status to the program office publicly, and we live stream it. That's so awesome. You can actually go and take a look on live stream at past years and see the keynote speeches and see all of these technologists talking about it. And so you can come to these meetings. Our next one, we're hoping to be in Tucson, Arizona. But it'll be live streamed as well, and so that's a really good highlight of the year to come take a look at that.
Wonderful. Well, we'll put links to the NIAC program in the show notes for this. And that's sort of a good starting place, I know, for people to want to sort of find everything else. So, Jason, thank you so much for taking the time to chat with us today. And so I hope for the people who are familiar with the content on my channel, now you know one of my biggest sources, one of my secret recipes for how I get so many of these ideas. They are NIAC programs. And so whatever happens, never, ever cancel the program again. I will, because I won't have any more content. So thanks for everything you guys are doing.
Well, thank you very much for having me. I really appreciate it.
All right. Take care. Thanks, everybody. Next week, it's probably going to be at a non-standard time as well. I think I'm interviewing some folks from the Ariel spacecraft, so stay tuned on that. Thanks, everyone, for watching today, and we'll see you all next week. All right, I'll stop the stream.